This is part 2.2 of my contractility analysis procedure in tissue. Picking up to some extent where we left off here, I didn't realize I had already reached the 30-minute cutoff limit for Clipchamp, but I think it's okay. In the interim, I analyzed all the other videos and analyzed most of these peaks here. So I'll just go over the rest of this. So um, I already manually identified most of uh, most of these as either peaks or not peaks, corresponding with what I see on the graph. And it looks like I left off somewhere around 16.8 seconds. So that's probably this. That's this here. That's that peak here. And then the next ones aren't making that much sense. It's contraction fall or relaxation followed by relaxation peak. And I think these are both. This is a beat together, so I'll try to hit both of those, 18.5 and 18.7. So I'll get rid of that one, and I'll include the 18.7 one. And now that's making sense. Relaxation followed by contraction there. That's good. That's a whole beat. And then next, analyzing these. Looks like 19.8, 20.7 are the ones jumping up to me. So let's try that. See if it looks better there. Looks like 19.8 would be another contraction peak, so that doesn't make much sense, so I'll get rid of that. Well, I guess we have a 19.6 here somewhere just below it, so maybe that does make sense, so I'll include that one actually. So we have that beat there, and then 20.7 and 21.3. Does that make any sense? So 20.7 would be there. 21.3 would be there, so that makes enough sense to me. And it's picking up this final peak as a relaxation peak there. So all of this, I think, is analyzed. I figured there are about 8 beats here. Did it up when parsing through this, so we got to 11.5 beats. Within a reasonable range, I think. And there's, of course, some subjectivity here as to where you want to place the cutoff. Do you really want to analyze this sort of thing? I would say some of these are kind of borderline. I think anything below 2 arbitrary units per second, I would be suspicious of noise. Definitely, you might want to go through and make sure there isn't anything below like 1. So there isn't anything below 1 here. And some of these peaks that are below 2 are kind of necessary in order for the beats to make sense. One approach you could do that I don't typically do is look at the videos and try to map that onto what you're seeing here. One issue of that is that it can be quite hard to see, like this is indeed faint beating, but that's definitely an approach you could use. And one thing that you might notice, which is rather interesting, is the amount of time between the contraction and relaxation. So we'll see if that makes sense. So this interval here, we'll see if that makes sense. And one of the ways I like to check whether this makes sense is looking at the value before the treatment. So before the treatment for this condition, I'll go over here. So this one got a shorter interval. So here the interval value doesn't look that bad to me. Looks pretty reasonable, consistent with that. Though keep in mind this is the interval between contraction and relaxation, and right now it's reporting the opposite. So if I were to, and sometimes you need to do this, go in and correct the formula, because the formulas I have here are for whether these peaks are starting with contraction, but here putatively it's starting with relaxation. And if we do it that way, then we get an unreasonable value for the interval. So I actually don't want to do that, so I'll click Control Z here to get back to how it was before, which means that the more reasonable value came when the reference frame setting here is false. So if I change that to false, this flips, and then these formulas, specifically this interval formula, is giving a reasonable value, I think, according to what it was before treatment. But again, you can always double check that, see if that matches with what you see qualitatively. All right, and now what's left to do is analyze all the other videos, which I actually did in between the time taking these videos. So then go ahead and paste these into another spreadsheet. So I have a spreadsheet here that contains all of my data. So what I did is this was the 15th experiment we did. So and this is the section for the initial, so 1 hour before the treatment and then 7 days after the treatment. And you can see I've already pasted in all the conditions except what I just analyzed. So I'll go ahead and paste that in here. Yeah, and then just to give some commentary on what we're seeing. So I think you might have noticed a lot of peaks appearing up in the analysis for this session. It's a bit unusual, some decent amount on the high side, I would say. Usually the beats per minute before the treatment is somewhere around 35 beats per minute. So we're getting double that within an expected range, but nonetheless, figured I'd point that out. And then I'll go in here and calculate the percent change over time. So I'll just paste this formula over. And what this formula does is that it'll calculate the change between this condition before and after. So the beats per minute went down. So this is 74% of the initial. So 62 divided by 84 is 74.5-ish. And then the standard deviation here, I like to just include all the information, is plus or minus 7%. Drag that over, drag it down to get all of it. And this really allows, and this is, as mentioned before, I like to, especially for the contraction relaxation speed, always normalize to the initial value. I think if it's meaningful to report, say, the beats per minute on their own, or the time between the contraction and relaxation on their own, 0.3 seconds here, whatever that is. But these contraction speed and relaxation speeds, I think, are best reported in terms of some sort of normalization, because saying 6.3 arbitrary units per second isn't really meaningful. And even if you do somehow convert that using the resolution and so on and get that into microns per pixel, in my experience, just knowing a little bit about these programs, just depending on what buried within MYOCYTER the parameter values are and so on, that value is just subject to a whole lot of variation. So I would not, if you ever read 6.3 microns per second in one of these papers using such an analysis method, I would be very skeptical that that's actually the real value. It could be an order of magnitude off in either direction, is my sense based on messing around with this a little bit. But these percent values, I think, are much more meaningful. You do still see a decent amount of variability. So this is the untreated control. For example, replicate 1, replicate 2. In the first replicate, the contraction and relaxation speed went down. In the second replicate, the contraction and relaxation speed went up. So we do see that variability. And I think probably there are some things you could do to minimize it. One of the things I've noticed is that if you keep the plate at room temperature, then the contraction relaxation speeds do go down over time. So definitely try to keep it at 37 degrees Celsius. The method we have could be improved for doing that. Right now, these videos were collected just using a conduction plate on top of the well plate lid. And so I think in the future, if there's some way to capture all these videos in a more controlled at 37 degrees Celsius, that's good. Without that, what I just tried to do was go in order. So if I captured this well first on, that experiment, I'm going to capture this well first on the next experiment. And since I'm normalizing it to that, hopefully the time it's spent at room temperature is also pretty constant, and that decay is pretty constant, and so you get a reasonable value in that way. But there might be some things you can do, making sure the brightness is the same with each of these videos, the orientation of the well is the same. That might reduce some of this, but there's of course always going to be a decent amount of variability. So overall, just make sure you're getting a lot of replicates in these studies. And just to give some commentary on this, this is pretty expected for the beats per minute to drop. About 25% is what I typically see. So that's within expected for the controls. So before the treatment is allowing the tissue to compact for 10 days. So 10 days after the cells are mixed with the fibrinogen and thrombin, we do the experiment about. And then we wait another 7 days, and in that 7-day interval, the beats per minute drops by about 25%. And this is a related metric, which is the time between contraction and relaxation. That tends to lengthen by about 25%. So it's slower in this way and kind of correspondingly slower in terms of transitioning from the contraction to relaxation. So at 25% higher value-ish for the untreated control is pretty expected there. And then typically we see these speeds pick up by about 25%. So, maybe 125%-ish. So stronger beating is what I would expect from the untreated control as it's left to age. The way I think about strong beating is in terms of power, power in watts, like force times speed, and this is of course one of the two components of that power, the speed component, which in summing up my data is tends to increase over time. But yeah, this variability is why replicates are important, of course, and with a lot of replicates, it does give you enough ability to do outlier tests. So I'll just show some of that there. So I don't think any of that data from 50% to 150% of initial would count as an outlier. Typically, what's registering as outliers is something like 300%. So that was this test here, something like 300% registered as an outlier for the beats per minute. Sometimes, even 0 is within expected for some of our treatments. So these zeros aren't actually registering as outliers because post-treatment we do see a drop in speed. But yeah, this 334% is registering as an outlier and so on. So I think getting enough replicas is important for distinguishing that. I think that is all I have to say on that. So I'll upload, I think, this spreadsheet additionally in case it's helpful to people.